Cek, 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 cek. Okay, morning. Good morning, everyone. I will wait a bit until the others come as well. Only 2 of you are watching this video, so I will wait a bit. Okay. Okay. Morning, morning. Okay, morning, morning. Who else are watching this? How can we see? Abiyat is here. Okay, I will wait a bit. Where's the other? Ah, Rafi is here. I was looking for you, Rafi. Good. How many of you? It's around 10 or 18 right now. Let's wait a little bit more, okay, before I start the class. Okay, I think supposed to be quite a lot of you coming today already. So I will start the class today. Test fit. How will the UTS conducted? We are still discussing about it. Okay, so later I will update you via WhatsApp group about this thing. Okay, I think it's supposed to be quite a lot of you coming. So I will start today's class then. In that case, today I will still continue about the internal force and internal moment. Okay, and I will review a bit about the things that we have discussed before. Okay, so previously we already discussed about this problem. Okay, as usual, whenever we try to solve the internal force and internal moment distribution, what you're supposed to do at the beginning is always try to find the reaction of the supports. Okay, so this is the previous example that we talked about. We can see here the support reaction. We can have it 2.4 kilonewton on the right and 1.6 kilonewton on the left. Then after that, we try to divide, we try to cut it, we try to create a section on where the part is continuous. What I mean by continuous is if there is no force or there is no concentrated force or concentrated moment. If it's just a distributed force, we can still make it continuous. Okay, so for this kind of thing, we can separate this particular problem into two different equations. The first equation will works from x equal to 0, this point, until x equal to 6 meter, this point. Then the second equation will works from x equal to 6 meter, this point, until x equal to 10 meters, this point. Something like that. So we always try to find which part is continuous. Okay, in this case, we have two continuous equation. We can't just create one continuous equation because there is a concentrated force in the middle here, 4 kilonewton. It will make the things uncontinuous and not continuous. That's why we have to divide it into two. The first part here, one equation, and the second part here, another equation. Okay. Now the first cut is between 1.6 kilonewton and 4 kilonewton at this region. Okay, we cut it anywhere that you want. That's why we define the cut happen at distance x from the left edge, like this. The distance from the left edge, okay, is x. Always that way, because we want to find the equation. Then after that, we solve using equilibrium, sigma Fy, sigma Fx, and sigma moment. Because there is no horizontal force there, so we assume that there is no normal force. Using sigma Fx, the normal force will be 0. The normal internal force will be 0. Then the internal shear force, we can calculate it using sigma Fy, like this. Okay, using sigma Fy, what we have there, 1.6 kilonewton going up, positive, and phi going down, negative. That's why our phi is 1.6 kilonewton. Okay, then the moment, okay, using sigma moment at the right side, we can get this equation. Counterclockwise positive, that's why m minus 1.6 multiplied by x equal to 0. Then we get that our moment is 1.6 x kilonewton meter, like this. Then after that, the cutting on the right for this part from x equal to 6 until x equal to 10 meters, okay, we cut it. We can either cut it using the left part here or the right part. In this case, we use the right part, okay, but because x is the distance from the left edge, the distance from the right edge become 10 minus x. That's why the distance from the right edge here become 10 minus x here. Okay, and then moment positive is clockwise here. Phi positive is going up. Then we can calculate for phi and m using sigma Fy. What we can get is phi is equal to minus 2.4 kilonewton. Then using sigma moment on the left, what we can get is moment is equal to 2.4 multiplied by 10 minus x kilonewton meters. Then after we get all the equation that we need, okay, the equation for the phi is like this and this. The equation for the moment is like this and this. This is for the first part from 0 to 6. This is for the second part from 6 to 10. Okay, then we can draw. We can draw the shear diagram, internal shear diagram, and internal moment diagram. Okay, and this is the results. Okay, when I told you about discontinuity, this is what I mean. You can see here that phi is continuous, right? From x equal to 0 until x equal to 6. Then, when we have this 4 kilonewton concentrated force, suddenly it jumps from 1.6 kilonewton to minus 2.4 kilonewton. Okay? And the gradient here for the moment is it changes, it change as well. But the jump is here. The non-continuity happened here. And you can see the delta here between 1.6 and minus 2.4 actually the same as the concentrated force, 4 kilonewton. Okay, that's the thing. That's the thing that I'm talking about uh, uh, the discontinuity whenever we have concentrated force or concentrated moment. Okay, the same as well. At the beginning, at the left edge, we have 1.6 kilonewton. And you can see that there is a jump there from 0 to 1.6 kilonewton. And on the right edge, we have 2.4 kilonewton. And you can see as well there is a jump there from 0 to minus 2.4 kilonewton. So whenever we have concentrated force, there will be a jump in our phi, in our shear force diagram. Okay, up until that point. Anyone want to ask question? That's what I mean about discontinuity whenever there is a internal force. Whenever there is a concentrated force and concentrated moment. Any question? Let me check. No question? Muhammad Arfan. Okay, let me turn it off first. Muhammad Arfan. Sir, why when we want to calculate phi and m between 4 kilonewton and 4.4 kilonewton from 1.6 kilonewton, the length is also x. Phi and m between 4 kilonewton and 2.4 kilonewton. Okay. You mean 4 kilonewton to 2.4 kilonewton. Okay, this one. Why? The length is also x. Okay, okay, the distance we calculate it from the left edge, always from the left edge. That's why here our x is from the left, right? So 0, x equal to 0 is this point, x equal to 3 meter is this point, x equal to 6 meter is this point, x equal to 8 meters is this point, and x equal to 10 meter is this point. So all the calculation is supposed to be from the left. That's why if you take a look at that, whenever we try to calculate for the right cut, okay, for this particular equation, and if we take a look at the right side of the cut, this one, okay, the distance there is not x, but the distance there is 10 minus x, because in this calculation, the distance that we measure is from the right edge to the cutting. Okay, from the left edge to the cutting is h. Okay, from the right edge to the cutting, it will be 10 minus x because the total length is 10 meters, and from the distance from the left to the cutting is x. That's why the distance from the right edge to the cutting will be 10 minus x, something like that. Is that answering your question, Muhammad Arfan? Any other question? Any other question? No? Okay. In that case, I will continue. Go, no question then. In that case, I will continue. This is one of the case that I want to talk about. Why there is a jump there. Yeah. Okay. Then I will discuss about another problem here. This is another case that we can discuss about. Okay. As usual, you can see if we have this kind of problem, always start with the support reaction. Okay. After calculating all the supports, we can find that R1, at pin joint, the support the reaction force is 653 lbf, and at the pin joint here, the reaction force is 257 lbf. That's after we calculate using sigma fx, sigma fy, and sigma moment. Okay, then using this free body diagram, try to see the continuous equation that we can create from this. How many continuous equation which can represent the whole distribution. Okay. From this to this, okay, we can represent it with one equation because the distributed force is continuous, linear, continuous. So there will be one equation here from x equal to 0 feet until x equal to 4 feet. It will be one equation there. But there, the continuity stops because the distributed force changes from linear into constant. Then we have to represent it with another equation. From x equal to 4 until x equal to 8, we have to represent it with different equations. That's our second equation. Then after that, the continuity stops as well here at x equal to 8 meters because the distributed force stops there. That's why we have to represent it with another equation, third equation. It's from x equal to 8 meters until x equal to 10 meters. Then after that, there is a concentrated force due to this particular roller. That's why the continuity stops as well there. So we have to represent it with new equation there. So it will be our fourth equation from x equal to 10 meters, x equal to 10 feet until x equal to 12 feet. This is another equation. So we will have four equations. The first equation is from x equal to 0 until 4 feet. Second is from 4 to 8. Third from 8 to 10. And the fourth one will be from 10 to 12. So we have to cut it at 4 different locations. Okay, the first cut, okay, the first cut is at the from x equal to 0 to x equal to 4, it will be like this. Because it's linear, okay, because it's linear, as long as we know the equation, okay, as long as we know the equation, we can find the concentrated force which can represent the distributed force. Okay. Just now, this one is 100 lb per feet at this point, then 0 here. Okay. So, and if you can see, this one is x per 4 multiplied by 100. Okay, x per 4 multiplied by 100 is the equation of the linear equation of our distributed force is x per 4 multiplied by 100. It depends on x. When x is get bigger, okay, the distributed force will get bigger as well. If x equal to 4 feet, the distributed force will be equal to 100 lbf. So that's why this equation is correct. Okay. So this is the distributed force at the right edge. Then the distance of the concentrated force, represented concentrated force, will be 2x per 3. Like this. Okay. Now, if we want to find the represented concentrated force, we have to find the area under the curve. The area under the curve, the distance from the left edge to the cutting is x. Okay, so you can multiply x with the length here, x per 4 multiplied by 100, then divide it by 2 because it's triangle. So x per 4 multiplied by 100 is 25x, right? 25x multiplied by x, so it's 25x squared divided by 2. It will be 12.5x squared. That's the represented concentrated force here at this point. And the distance is 2x per 3 from the left edge. Then, after that, we can calculate for phi and m. Okay, using sigma fy equal to 0, the phi will be 12.5x squared is from this one, the concentrated force, the represented concentrated force of the triangle distributed force, plus phi, going down is positive, okay, minus 247 is equal to 0. So our phi equation is this. Then our moment to the right edge, this one, our moment to the right edge, counterclockwise positive, so m plus 12.5x squared multiplied by the distance here. The distance here is only x per 3 because from this to this is x. From the left edge to the concentrated force is 2x per 3. So this one will be x per 3. So 12.5x squared multiplied by x per 3. Then the last one will be 247 lb f multiplied by the distance here, x. So this is your moment. Okay, and this is the equation, final equation of the moment. 247x minus 4.17x to the power of 3. So if we draw it, if we draw the shear force diagram, it will be like this. If we draw the moment diagram, it will be like that. Okay. Until this point, anyone want to ask question? Hotel Trivago. What do you mean by that, Rafi? Okay, why do we have to cut it into 4 parts? Because we can't represent the whole equation. We can't represent the whole beam with only one equation, Rafi. Okay, you can see here. Just now I explained the OED. From x equal to 4 to x equal to 0 to x equal to 4, there will be one continuous equation because the distributed force is continuous. Then, because at x equal to 4, the distributed force changes from linear to constant, the continuity of the first equation stops there. We have to change with another equation. So we have to represent the second part here with another equation. Okay, then at x equal to 8 meters here, the distributed force stops. That's why the continuity of the second equation stops as well. That's why we have to represent the third part here from x equal to 8 until x equal to 10 as another equation. Then after that, there is a concentrated force due to the roller here. That's why the continuity stop as well there. Okay, the continuity stop as well there. That's why we have to represent the last part here with another equation. So total, we have 1 here from x equal to 0 to x equal to 4. Then from x equal to 4 to x equal to 8 is another equation. From x equal to 8 to 8 to 10 is another equation. Then 10 to 12 is another equation. Do you understand that, Rafi? I don't understand where 12.5 x square come from. X per 100 come from. Okay, why 12.5 x square come from? Okay, x per 100, I don't have x per 100 there. So what I have here is x per 4, x per 4 multiplied by 100. Yes, this is the distributed force. This is the distributed force at x. Okay, why it's like that? I think I need to explain to you. Just now, we know that at the end of the 4 feet, the distributed force value will reach 100 lb per feet. Okay, so this is the first part. Okay, the distributed force will follow like this. At the end of the first part, this one is 4 feet. At the end, okay, the value here will be 100 lbf per feet. Okay, now I want to find the equation of this particular distributed force. Okay, how can we find that? We need, this one is linear, right? If you have a linear equation, you can find it. Your equation there will have to follow the W, right? The W is supposed to follow this equation because it's linear, right? And we know 2 points here at x equal to 0 and x equal to 4 feet. Okay, at x equal to 0, we know the W at x equal to 0, the value is equal to 0. And we know as well that the W at x equal to 4 feet, the value is 100 lbf per feet. Using these two data, we can get A and B. Let's try. At x equal to 0, okay, if x equal to 0, we substitute it to this point, what we will be able to get is 0 plus b is equal to 0, right? Because the w here, the value is 0, and x is equal to 0, we have to put it here. So the first equation is 0 plus b is equal to 0, so b is equal to 0. Then, using the second equation, we can substitute x equal to 4 to this. Okay, we will be able to get that a multiplied by 4 plus b, which is equal to 0, supposed to be 100. The w is equal to 100. That's why our a will be 100 divided by 4. In this case is 25. Okay, so our equation now, the a is equal to 25, b is equal to 0. So our final equation is w equal to 25x plus 0, which we don't have to write down. So this is your equation for w. W is equal to 25x. That's why here you can see, okay, the w is the same as 100x divided by 4, which is the same as 25x. Okay. Okay, so I answer Abiyat question already. Now, how did you get 12.5x squared? Okay, 12.5x squared come from, let's check again here. Now, because this is the first cut, I cut it here. Anywhere between x equal to 0 and x equal to 4. I cut it there. And the distance from the left edge to the cutting is x. Okay, so now I will redraw the free body diagram. The distance now become x, and this is our distributed force. And our distributed force will follow this 25x. Okay. $25x. Okay, as usual, at the right cut, we have phi going down positive and moment counterclockwise positive. And on the left edge, we have the external force from the pin. Okay, from the pin, 247 lbf. Okay, 247 lbf. Okay, I believe that I told you from the beginning that if we have a triangle distributed force, the representative concentrated force will be at the centroid here. This is the centroid, and the centroid, it will be 1/3 from the right and 2/3 from the left. That's why the distance here will be 2 per 3, 2x per 3. From the right will be x per 3. Now, why the concentrated representative force, the value is like that? Remember that the concentrated representative force it's supposed to be the area under the curve, okay? The area under the curve, and if we have a triangle, the area of the triangle will follow, okay, the length here multiplied by the length here divided by 2. So in that case, I have 25x multiplied by x divided by 2. And it will be the value of my concentrated force, 12.5 x squared. This one. So now I can redraw the free body diagram for this case into like this. That's the thing. Does this answer your question? So A is like the distribution of the force. No, A and B there just now. Okay, A and B is this one is a linear equation. Just the same as if you have a linear equation, y is equal to ax plus b. This is a linear equation. My y here is not y, but w, because it represented the distributed force. Okay, and in order to represent a linear equation, we have two constants, a and b, right? A and b. Using the value that we know, at x equal to 0, the w is 0, and at x equal to at x equal to 0, the w is 0, and at x equal to 4, the w is 100, because we know this value already from this, from the first, from the problem they given to us. Okay, we can put it here in order to find out the a and b. When x equal to 0, okay, the w is 0, it will be one equation. Okay, and what you will get there is this. Okay, sorry. And from this, when you put it there, what you will get there is this. A is equal to 25, B is equal to 0. Okay? Any other question about that? Any other question? Let me check. Okay, no more question. Okay, in that case, let's continue. So, this is the results of the first cut, okay, from 0 to 4, from 0 to 4 for the phi and from the moment. Okay, that's the equation. This is the equation for phi, this is the equation for m. Okay, in order for us to know where's the exact point at x equal to 4, what you can do is you can substitute 4 to this in order to know what is the value here at this point. The same, you can substitute 4 here in order to know what is the exact value at this point. Okay, then After that, we continue with the second equation from 4 to 8. Okay, from 4 to 8, now we cut it here. Okay, we cut it between 4 to 8. Okay, and the concentrated force, it's supposed to be exactly in the middle. Okay, it's supposed to be exactly in the middle. And for this one, because it's already finished, it's supposed to be represented by the area under the triangle, because it's already finished. So this one is 100, the distance is 4. So 100 multiplied by 4 is supposed to be 400, divided by 2 is 200. And we're supposed to put it at 2/3 from the left. Okay. Then after that, we can calculate using sigma Fy at sigma moment to calculate for phi and m. Okay. Remember, just now the distance from the left edge to the cutting is x. Okay. But this particular distance, it's supposed to be x minus 4. Okay, why x minus 4? Because the distance from this particular point to this particular point is 4 feet. That's why if this particular point to this particular point is x, this distance is supposed to be x minus 4. And the middle of the x minus 4 is supposed to be x minus 4 divided by 2. So the distance here from the represented concentrated force, this one, to the right edge is supposed to be x minus 4 divided by 2. And the area there, because just now the W is 100, okay, lb per feet, okay, we're supposed to multiply 100 with the distance from this to this, which is x minus 4. So this is the representative of the concentrated force, 100 multiplied by x minus 4. Okay, then after that we can calculate for phi and we can calculate for m using sigma Fy equal to 0. If going down is positive, phi is positive, 100x minus 4 is positive, 200 is positive, minus 247 because it's going up. What we will have there is phi is equal to this equation. Using sigma moment at the right equal to 0, okay, there are 3 components there, this one, and this one, okay, and moment as well. So if clockwise is positive, that's why we have m is positive, then 100x minus 4, the concentrated force here, this one, multiplied by the distance, x minus 4 divided by 2, this one, okay, plus 200 multiplied by the distance from the right edge. The distance from the right edge will be x minus 4, this one, plus 1/3 from the fourth. So x minus 4, yeah, plus 1/3 from the right. So this is our result. And your final equation will be like this. Okay, and then we draw it here, continue the drawing like that. Okay, the same thing, you're supposed to do that as well for the third cut and fourth cut. But in order to make it easier, the third cut, we can analyze it from the right instead of from the left. The same for the fourth cut. We can analyze it from the right instead of from the left. And at the end, what you will get is this kind of distribution. Now I should remind you again that whenever we have concentrated force like this, there will be a jump in our V. And we have another concentrated force like this, there will be a jump there as well. And the jump there supposed to be exactly the same value as our concentrated force. Okay, I know that this problem is slightly more complicated. Okay, so later, after the class ends, it is better for you to review it again, especially for the this particular part for step 4 and for step 5. That's the thing. Okay, any question there? Who's coughing, sir? The one who's coughing was not me. Okay, the one who's coughing is my wife. Stay safe and healthy. Yes, thank you very much. Okay, if you don't, who will taught us? Okay, thank you very much. Okay, any other question about this? Okay, the things that I want to highlight today is beside reviewing how can we draw the internal force distribution and internal moment distribution is whenever we have a concentrated force, okay, external concentrated force, there will be a jump in our shear force diagram like this. At this point, there will be a jump, and the jump there is the same value as this, 247 lbf, and then another jump here from this point to this point. At the jump there is the same as this as well, 653 lbf, from minus 353 until 300. So the jump there is the same. Then another jump there as well at the end, from 300 to 0, the same as this one. Okay, so that's one thing that you're supposed to know whenever you draw the internal force and internal moment diagram, and how can we confirm whether it's correct or not. Okay, and I should tell you as well, sorry, there is another problem example as well. So this will tell you what's the difference between these four. Okay, whenever we have these four cases, it can tell you what will concentrated force give to the internal force and internal moment, and what is the concentrated moment will give to the internal force and internal moment. Okay, you can see here, if we try to solve all the external force at the roller and the pin, okay, external force at the roller and the pin, what we will get is like this, roughly like this. Okay, PP there, P is our external force, and the reaction force will be like this. Okay, then B, there will be P going down and P going up, right? Same here, P going down, P going up, and our reaction force will be like this. Okay, then at C is just a moment, one moment in the middle, like this. Our reaction force will be like this. At D, two moment at both edge, and our reaction force will be like this. For this reaction force, what you can do is just to solve it using sigma Fy and sigma moment, and you will be able to get all of this reaction force. Okay, but my point is not like that, but my point is I want to show you at the end, okay, if you already draw the free body diagram, if you already draw the free body diagram and you did all the cutting and you draw the internal force distribution, this is what you will get. Roughly, this is what you will get. And this is, as I told you before, whenever we have external force here, there will be a jump here. Another concentrated force here. There is another jump here. Concentrated force here. Another jump here. Concentrated force here. Another jump here. The same as this one as well. The jump will be exactly the same value as our concentrated force. But if you see here, there is a concentrated moment. There will be no jump in our moment diagram. There will be no jump in our shear force diagram. The same here, there will be no jump in our shear force diagram. It stays 0. But if we take a look at the moment diagram, at the end, the results of the moment diagram, okay, due to this particular concentrated moment, okay, as you can see here, exactly in the middle, there will be a jump in our moment diagram. The same at D, because of this concentrated moment diagram, there is a jump at the beginning. And at the end, there is another jump due to this particular concentrated moment here. And the value of the jump is exactly the same as our concentrated force and concentrated moment. So in the phi distribution, the jump there will be based on the value of our concentrated force. And in the moment distribution, the jump there will depend on the value of the concentrated moment. And because of concentrated force, there will be no jump here in the moment diagram. The same as here as well, there will be no jump there in the moment diagram. But the opposite happen as well. Whenever we have whenever we have concentrated moment, there will be no jump in the shear force diagram. The same here, there will be no jump in the shear force diagram. So that's the thing that I want to talk about today actually. Any question? So that's one of the way to ensure that you did everything correctly. To check whether the jump is correct or not. Okay? Any question? Any question there? Let me check from my YouTube account. No one is asking question. Okay, and one more thing, I will tomorrow after the class tomorrow we will start the class at 1 p.m. until 3 p.m. Okay, at the end of the class I will give you a homework about this because practice makes perfect, especially for this internal force. Okay, you have to keep practicing because more practice you will get used to it. Okay, terang berantas. Physically, why is there a jump? Yeah, because that's, I told you from the beginning, the concentrated force, concentrated moment, it will cause the discontinuity on the distributed force diagram and distributed moment diagram. Okay, and the continuity there will be in the shape of the jump. And the jump there will be exactly the same as the concentrated force. Actually, you can explain it by yourself uh, if you try to cut it there. Okay, for example, okay, it's too messy here. Okay, for example, if I cut it here, the results of my free body diagram will be like this, right? P going up, then phi, then moment. Okay, it's P. Our phi there, using sigma Fy equal to 0, my results will be equal to P. Okay, right? And at this point, then I will cut it again at that point. It's slightly longer. There will be P going up and P going down, and then phi here and moment. Using this one is P as well, P as well. Okay, using sigma Fy equal to 0, what will I get there will be phi is equal to 0. Because it's P going up minus P going down minus phi is equal to 0. So what I will get is phi equal to 0. So basically, this equation works for this side. And this equation works, the second equation works for this part. So you can see there is a jump there automatically. And the jump there will be the same value as this one. Okay? Any other question? Before I close up the class. It's more and more. Okay? After this, I will give you one problem example, another problem example. I will give you several problem example and you have to watch it before tomorrow class. Okay, so tomorrow what will I do is just answering your question about the video and about the things that you don't understand yet related to the uh, distributed internal force and distributed internal moment. Okay, I think that's all for today. Okay, don't forget to check your WhatsApp group because I will post the YouTube link there. Okay, see you guys tomorrow.